So, questions? All right, well, let me talk a little more about standard in and standard out and some of the details of that. So we said you can run a command and use a less than sign to feed input into that command, right? And we also said you can run a command like PS, which shows me programs that are running. You can use a greater than sign to take the output of that command and put it into a file, and so you can capture output like that. And you can also use two greater than signs to append to a file. So if I do date greater than file, and I look at my file, it's got the previous contents, which was from PS, and it's also got the date in it, and that can be useful. The other thing is, and tell me if I already said this, I said it in the second section, I don't think I did in this one. So this is redirecting standard in. These are redirecting standard out. There's actually a third channel that we can do I/O on besides standard in and standard out. There's this thing called stderr. So if I try to compile this program, haha.c, I have a bunch of errors, right? And it's nice to be able to sometimes take your error messages and put them in a file so you can look at them or save them or whatever. If I try to do that with a greater than sign, it doesn't work, right? I still see my errors on my screen, and if I look at my errors file, nothing got written into that. And the difference is when GCC prints out an error message, it doesn't send it to standard out. It sends it to something called stderr, S-T-D-E-R-R. And normally, standard out comes to my screen, standard error comes to my screen. When I say command greater than file, standard out gets redirected to a file. Standard error still comes to my screen. So if I say command, and then I say greater than ampersand without any spaces, file, that redirects both standard out and standard error. And so if I do my GCC command, but instead of a greater than, I say greater than ampersand, now all that output from GCC goes into a file. And I can go through that file and see what the error messages were. Alright, so standard in, standard out, standard error. And we can redirect to or from files like this. The second thing we can do is we can use pipes. So we can type command 1 and a pipe, command 2, and that takes standard out from here and feeds it to standard in on that command. So it's kind of like saying command 1 greater than file and then command 2 less than that same file, but without having a file in the middle. And we've played a little with this before. So for example, if I say ls-l, I see a list of files in here. If I put that into a file, there's my file. If I say word count file, I can see that there's 4 lines of output in that file, right? If I want to put those two things together, I could just say ls-l and pipe it into word count. And so the output of ls goes into the input of word count. And so we've done this with things like take the date and pipe that into cow say, and the cow tells us the date. Or the cow shows us what our files are. So pipes are extremely useful for combining commands in all kinds of ways. And when we talk about some more Unix utilities, awk and sed and things like that, we'll start doing a lot of piping commands together. And so if I gcc haha.c, right, all my output scrolls off the screen. We have this program called more that we can take input and display it one page at a time, right, which is kind of useful. So we could try to take gcc, well, let's do this. Right, so if I do an ls-l on /bin, it's a bunch of information, right? I can take the output of that and pipe it into more, and now I'm seeing the output of ls-l/bin one page at a time. So there's the first page of output. I can hit a space bar and see the second page, and I can go down just by hitting space, and so on. And the same thing with gcc haha.c, all those error messages are going to standard out. Well, that pipe connects standard out to standard in, so if I do that, I still get all my error messages coming to the screen. Nothing went into more. So same trick as with the greater than sign. If we do a pipe with an ampersand, that means connect both standard out and standard error from gcc to standard in of more. And now our error messages are showing one page at a time. So I don't have to scroll back to find the first error. It's sitting right there at the top of the screen. And I can scroll through a line at a time, or a page with a space. So pipe connects standard out to standard in. And with an ampersand, both standard out and standard error get connected to standard in. And you can keep doing these pipes, right? I could do ls-l, pipe into word count, and I could pipe that into some other command, or I could take the result of that and I could send it to, an output file. And now that's got the output of word count after you feed the output of ls-l into its input. So you can just string these things together in all kinds of ways. And like I said, we'll use those more in another week or so. Alright, the other thing we need to talk about is backquotes. So backquotes are these characters. For me, they're sitting to the left of the one button. They're the unshifted version of a tilde. So single quote and double quote are on the same key, right? Double quote is easy to tell. Single quote is kind of a forward quote, sort of like a forward slash. Backquote is different. And backquotes have a special and powerful meaning in Bash. So if I say echo double quote date, it just shows me date. If I echo single quote date, it just shows me date. If I echo backquote date, it shows me the date. That's a little weird. If I say x equals double quote date, and I echo x, it's just date. If x equals single quote date, and I echo $x, it's just date. If I say x equals backquote date, and I echo $x, it's the date. And it doesn't change, it's just a variable. It's always going to be 101456. But if I again say x equals backquote date, now it's the date when I said x equals backquote date. Okay, so here's what's happening with these backwards quotation marks. X equals backquote command does the following. It executes this command, and it sets x equal to whatever is sent to standard out when command executes. So when you use backquote command, basically the command runs and this backquoted thing is replaced by the output from that command. So if I say files equals backquote ls-l, files is a variable that's equal to, you know, all the output from the ls-l command. And there's a cow that's been like sliced and made horizontal. So if your command outputs multiple lines, they all come out side by side on one line. But this is useful for a lot of things, right? If you want to know what directory you're in, you can set a variable equal to backquote pwd, and now that variable is the directory that you're sitting in when you executed that command. So I can set x equal to backquote ps pipe into word count. PS shows me how many processes I have running on the system, and word count counts up how many lines of output are generated. And so x is equal to 5. So I apparently had 5 processes running when I did that. So that's another thing we'll come back to when we'll use to tie commands together. And do some more powerful things in Unix. Alright, so I suggest experimenting with that. Play around with it, but we'll see some uses for it later. Any questions on the ODP that was done this morning? 420? Okay. Alright, so let's talk about sorting. So let's do bubblesort. So my mental picture of why this is called a bubblesort, picture a bunch of rocks being dropped into water. And the rocks are very heavy and they fall down to the bottom, and the bubbles are very light and they bubble up to the top. That's kind of what goes on inside a bubblesort. We start off with just a bunch of numbers. So we'll sort that array of numbers. So there's a lot of ways to sort things, right? 222 we'll spend a whole week talking about different sort algorithms. Bubble sort is one of the first ones that people learn. It's almost the only sort I've ever actually coded up myself in day-to-day use, outside of like class assignments, because it's pretty fast, you know, for a reasonable amount of data. If you want to sort, you know, a few thousand numbers, you can use a bubble sort. It works fine. If you want to sort your phrases by length for PA4, bubble sort works great. If you wanted to sort 1 billion numbers, bubble sort's not a really good way to go. Okay, it's going to take a really long time. And there's other sorts that will let you sort 1 billion numbers pretty efficiently, but they're more complex. algorithms. But bubble sort's a really good go-to. So it's a good one to know and be able to pull out, especially like, you know, in a job interview or something. So the basic setup for a bubble sort is built around a series of passes. So we have 1, 2, 3, 4, 5, 6, 7, 8 pieces of data. Okay, more generally n pieces of data. So a bubble sort basically makes n passes. N times that we're going to move through the data and rearrange things. And the goal is each pass we move the largest number to the bottom. So our first pass through a bubble sort is going to find the largest number in this list and move it to the bottom. Let me put in some more numbers because I unfortunately put the largest one at the bottom anyway. So we'll throw in a 5 and we'll throw in a 0. Alright, so here's how a bubble sort works. It looks at pairs of numbers. It starts with the first number, and we want to sort from smallest to largest. So it looks at the 4 and looks at the 2 after it, and it says, are these two in the right order relative to each other? And they're not. The 4 is bigger than the 2. They should get swapped. So this becomes a 2 and a 4. And now it looks at the 4 relative to the 3, and those are in the wrong order. So those get swapped. So this is a 3 and a 4. Looks at the 4 versus the 7. Those are in the correct order. So the 7 will stay here. Looks at 7 versus 1. Well, that's in the wrong order. 1 should come first. So that becomes a 1. This becomes a 7. Then looks at 7 versus 6. Those are in the wrong order. So this is a 6. This is a 7. Looks at 7 versus 8. Those are correct. Looks at 8 versus 9. Those are correct. Looks at 9 versus 5. Those are backwards. So that's a 5 and that's a 9. And then looks at 9 versus 0. That swaps 0 and 9. So after our first pass, if we clean this up, our data looks like 2, 3, 4, 1, 6, 7, 8, 5, 0, 9. And here's what we know. We know that this number is in the correct spot. If we make another pass, and we just think about these first n-1 numbers, if we do the exact same thing when we're done, the largest of these numbers should be sitting right here. It's not going to be bigger than this because this is the largest of all. So the next heaviest number, the next largest number, should sink all the way down to the bottom here. Okay, and this has got to work, right? If there was some number up here that was bigger than 9, right, it should have been swapped with everything below it. And should have kept swapping until it eventually got down and was compared to the 9, and then it would have swapped with that. So to formally prove that this works takes some work, but just kind of intuitively, it should make some sense that each time we make a pass, the largest thing up here is going to move down to the bottom. So if we make a second pass, well, 2 and 3 are in the right order. 3 and 4 are in the right order. 4 and 1 should swap. 4 and 6 are in the right order. 6 and 7 are in the right order. 7 and 8 are in the right order. 8 and 5 should swap. 0 and 8 should swap. And the 9 should stay there. And now we got two things in the right spot. Well, if we have n numbers and each time we make one of these passes, the next largest number goes into the bottom of the output, right? Theoretically, after n or maybe n-1 passes, everything in here should be sorted. So if you have n numbers, you really only need n-1 passes. But you know, even if you do too many passes, it takes more time, but it doesn't disturb the result. If all my numbers are sorted and I make another pass, nothing's going to change position. right? So a lot of times when you code this up, you just say we're just going to do n passes. And each pass we're just going to loop through and compare each number to the one after it. So this is pretty easy to code. And when you code it up, it generally ends up looking like a pair of nested loops. So here's our inner pass. Alright, so let's suppose we have n pieces of data stored in an array called data. And we'll just work on integers. So we have data bracket 0, data bracket 1. What's the index of the last element in this array? It's actually n minus 1. Good, because we start from 0. So what are we going to do in this inner loop? We're going to compare data bracket I with data bracket I plus 1. And we're going to swap them if they're out of order. So if our largest thing we want to compare with is n minus 1, we actually only want to go up to n minus 2. So this is actually while I is less than n minus 1, I plus plus. Because if I is equal to n minus 1, then I plus 1 will be n, and we'll start comparing something with data bracket n, and that doesn't exist. So we might segfault, we might compare with something meaningless. Okay, so let's see if data I is less than data I plus 1. And if it is, then we don't have to do anything. But if it's not, then we need to swap. So if data bracket I is bigger than or equal to, well, we don't really need to swap if the two things are equal, right? Because swapping wouldn't do anything, so we really can just check for greater. So this is out of order. So if data I is bigger than data I plus 1, we need to swap them. So how do we swap two variables? If we have variables a and b, how do we change it so that b is equal to a and a is equal to b? Right? In Verilog, this would work. Right? We could say a equals b and b equals a. But this doesn't work in C because as soon as we say a equals b, b is now being set equal to whatever b already was. It doesn't actually set b equal to the old value of a, because a has changed value. So the easiest way around this is before you change the value of a, save it somewhere. So save a equals a, and then you can change a equal to b, and then you can set b equal to the saved value of a. So this is something you'll see a lot. You want to swap two things, save one of them a temporary, change the thing that you just saved to be the other thing, and then set the other thing to the temporary. Bonus question, can you do this without the temporary variable? You actually can. So that's something to play with. I had a student get angry at me for this once. He thought it was an ugly solution. It is an ugly solution, but it is doable, so it's fun to play with. See if you can figure out how you can swap two integers in a C program without using a temporary variable, without writing one out to disk or anything like that, just using the two variables. It's actually doable. But we'll just use a temporary. Alright, so there's our swap. And there's the end of the inner loop. So that represents one pass through our data. And at the end of that, everything should be in the right place. So we need an outer loop. So there's bubble sort. And if you wanted to make this a function, right, so pass it the array of data, that's an integer star, and pass it how many pieces of data are in that array, that's what n is. And then the rest of this should work. You've got to declare your integer I, integer j, and integer temp. But right, so this makes sense, inner pass, outer pass. This moves one thing into the correct spot, and you do that n times, and your whole array should be sorted when you're done. And you can make this more efficient a variety of ways. For example, after we've done one pass, we know this last number is in the right place. The next pass, we don't have to actually go through all of the data. We never need to compare that next to the last element to the last one, because we know the last element is bigger. So for the first time through, we need to go up to n-1, but the second time, we really only need to go up to n-2. And the third time, we really only need to go up to n-3. And when this thing is almost sorted, and we're doing our last pass, we really just need to compare the first two elements to each other and see if they need to swap. So this inner loop could get smaller and smaller, which makes it faster and faster. And the outer loop, we only really need to do n-2 times. So we could shrink that down. We can also speed it up by noting that if we ever make a pass through here and we don't change the order of any of our numbers, we're done. Everything is sorted. And that could happen, you know, if I did a bubble sort on a set of data that was already sorted, I'd make one pass through, and since nothing changed, I'd know that I was done. So we could embellish this by using a flag. So we could say done equals did stuff equals 0, and then inside here, whenever we swap something, we'll just set this flag. Say did stuff equals 1. And then instead of having a for loop up here, we could say while we did stuff. And so we'd initialize did stuff to 1 so that it does it at least once, right? So we'll go through here, we'll do our while loop, we clear this flag, and we only set it if we actually do some stuff, if we swap things around. If we make a swap, did stuff will be 1. When we come back to the top of our while loop, we'll make another pass. But if we go all the way through this for loop and we never set did stuff to 1, we never swapped anything, when we finish that while loop, did stuff will still be 0, and we'll exit our while loop the next time through. So this will just keep making passes as long as those passes change at least the order of one pair of elements. And the first time we go through and we don't swap any elements, did stuff will be 0, and we'll exit our while loop. So that makes it more efficient. Alright, so got the idea of bubble sort? And I think you've seen this before, so this is just a different view of it. But let's look at how long it takes a bubble sort to work. So forget about the embellishments, forget about the did stuff flag. Let's just have a loop on the outside that runs n times and an inner loop that runs, let's just say, n times. Forget about the n minus 1. How many times are we looping total throughout the whole bubble sort? How many times do you think we look at, say, this if statement? And let me clean the code up for you.
Do you mean with or without reducing the...
Without any of those simplifications. So how many times do we execute stuff?
Would it be n squared?
What do you think? How many people vote for n squared? Only one vote. 2 votes, 3 votes, plus the original. Yes. So it's basically n squared. Because this inner loop, we're going to execute stuff n times, right? Assuming nothing exits or returns partway through. This loop right here, we're going to execute stuff n times, and we're going to do this loop n times. So first time we do n stuffs, second time we do another n stuffs, third time we do another n stuffs. After n times we've done n stuffs n times, that's n squared. And what do we do in here? Well, we do an if statement, and you know, if this data is not bigger than that data, we don't do any of these things. It's an if statement that we don't do the body of. But if things are out of order, then we have to do some more stuff in here. We have to do 3 assignment statements, right? Possibly 4. But when we look at the efficiency of algorithms, we're not really trying to measure how many microseconds or nanoseconds is this code going to take to execute. We're really interested in how does the performance of this code change as the problem size changes. We're interested not how many seconds does it take to sort 1,000,000 numbers, but we ask the question, how much worse is it to sort 1,000,000 numbers than 1,000 numbers? Or if we know how long it takes to sort 1,000 numbers, what happens if we sort 1,000,000,000 numbers? Does it take twice as long? Does it take 10 times as long? Does it take 1,000,000 times as long? Okay, because, you know, computers change speed. If I go back to the 80s and I run this on a computer, it's going to take a lot longer than if I run it on my laptop today. And so coming up with these bare measures of time, right, isn't necessarily meaningful. If I write this in assembly language, it may run faster than if I write it in Python. But what's not going to change is for this algorithm, how many times am I doing this stuff inside? It's basically n squared. And you can kind of see that from here, right? I have basically n comparisons I have to make, and I do this n times, it's basically n squared. Now, in reality, if I use my embellishment, right, and I say, well, once this first number is in the right spot, I only have to look at these top numbers now, and then I only have to look at those numbers, right? So the first time through, I might make n comparisons. The second time through, I'm only going to make n minus 1 comparisons. The next time I'm going to make n minus 2, n minus 3. I'm going to do that until I come down to just two numbers left, and I just make two comparisons. So the number of times I'm going to have to do stuff is roughly the sum of the integers from 1 to n. It's actually 2 to n, but we're being approximate here. So you remember the formula for this sum? Sum of the first n integers? So something like n times n plus 1 over 2. So if we embellish this, instead of doing n squared operations, it's actually going to do n squared over 2 plus n over 2. Which seems smaller, right? This is this is half of n squared plus a little bit. This is n squared. It turns out, in terms of how much worse this algorithm gets when the problem size grows, it doesn't matter if we think of this as n squared or n squared over 2 or n squared over 2 plus n over 2. We're going to see the same basic behavior, which is something we call order n squared. All right, so let's see what order n squared means. So let's just imagine that we're doing n squared operations to sort n pieces of data. So if we're sorting 10 pieces of data, we're going to have to do that stuff in the middle of our loop basically 100 times. If we have 20 pieces of data, we're going to have to do that inner stuff 400 times. If we have 100 pieces of data, we're going to have to do that stuff 10,000 times. Okay, compared to our original case, 10 pieces of data, 100 operations, when we have 20 pieces of data, we've doubled the amount of data. We've got 2 times as much data. What happened to the amount of stuff that we had to do our bubble sort went up by 4x. When we went from 10 to 100, our data increased by 10 times. The number of things that we had to do our sort went up by 100 times. Okay, this is what order n squared means. It means when you double the amount of data, the amount of time your algorithm is going to take goes up by not twice, but by 4x. 3 times as much data, 9x. 4 times as much data, 16x. Okay, that's where the n squared is coming in. If you increase your amount of data by k, you increase your computation time by k squared. That's the basic behavior. Now suppose you have a fancy algorithm where the amount of stuff you have to do is just n squared over 2. So to bubble sort 10 pieces of data is only going to take 50. To bubble sort 20 is going to take 200. To bubble sort 100 is going to take 5,000. Right? Seems like a faster algorithm, and it is faster. It takes half as much time. But again, we double the amount of data, our computation time goes up by 4. We go 10x more data, our computation time goes up by 10x. Sorry, by 100x. So it's still this n squared behavior. Okay, that's what this big O, this order of complexity, is capturing. So bubble sort is an order n squared sort. Meaning if you can sort 1,000 pieces of data in a second, 1,000,000 pieces of data, which is 1,000 more, is going to take you 1,000,000 seconds, which is a long time. So sometimes in 215 and always in 222 we spend a bunch of time talking about order of complexity, which we just write as this script O. And order n squared is bubble sort. It's really not a very efficient way to sort things, but again, we don't care for 1,000 phrases in a dictionary. It's fine. Order n is really nice. That's linear. It means if you double the amount of data, you double the amount of time it takes. That's pretty nice. That's kind of an ideal that we rarely achieve. Order 1 is really utopia. Because order 1 says, if I can sort n pieces of data in this much time, I could sort twice as much data in the same amount of time. Which means I could sort 1,000,000 times as much data in the same amount of time. Order 1 is an algorithm that always takes the same amount of time, no matter how big the data is. And that's really cool. That's nirvana. And we have some algorithms that theoretically give you order 1 performance. The only thing that might be slightly better, and I don't think people actually talk about this outside of bars maybe, would be order 0, which is an algorithm that takes no amount of time no matter how much data you have. Is that possible?
And how useful the algorithm is.
Yeah. I suspect there's some order 0 algorithms out there. One of them might be called the universe. So other things that we'll encounter, you'll find order n cubed algorithms. Those are even worse than n squared. Doubling the amount of data takes 8 times as long. But this is still considered desirable sometimes compared to this, order n factorial, or order n to the n. So order n to the n is horrible. If you have 10 times as much data, just 10 times as much data, it takes 10 billion times longer to execute. So compared to that, n cubed is pretty sweet. But a lot of algorithms turn out to be this order n to the n, for example. And that's pretty horrible. And so there's things like the traveling salesperson problem. I think that breaks down to an n to the n complexity. And some of these algorithms, if you can find something like order n cubed or order n to the millionth or order n to some finite power, you can write that up and get $1 million for it through the Millennium Prizes. All right, so that's something we'll come back to repeatedly throughout this sequence. And you don't need to know all this to do a bubble sort. Just code up a bubble sort and live with the order n squared. But there are other things out there. All right, so what are we going to do tomorrow? Tomorrow, let's start outlining some flowcharts. Let's start doing some flowcharting for more of PA4. Let's look at breaking phrases, breaking up input into phrases, and we'll do a flowchart for that. And that should be a good launch into the weekend. Remember, no class on Monday. It's a holiday for Clark, so you got Monday off. All right, I'll see you tomorrow.